Hello everyone, my name is Hasan Zerze. I would like to talk about why Lorentz transformation must be a linear transformation. If you remember in my previous video, I derived the Lorentz transformation laws, but I assumed in those derivations that transformation is linear, and we made an assumption there. This time, I would like to show you why this must be the case, why Lorentz transformations must be linear. So I would like to draw a person here, which represents the frame of reference A, and then say we have another person in the frame of reference B, and this frame of reference is moving with a speed of v along a certain direction. And we talked about, two events being separated with a time difference of delta t and a positional difference or displacement of delta x. And then we talked about how this process is viewed in the framework of the person B. And we said that it must be delta t prime, delta x prime. And we said that the transformation that takes from delta t, delta x to t, delta t, delta x, which is delta t prime, delta x prime, must be a linear transformation. Now, imagine that we have one vector like this. When I say vector, I talk about this separation in the time and the separation in the position. Let's call this one as, say, vector W. Okay, and then this is vector W, and then let's call this one W prime. So what this transformation is doing, T W happens to be W prime. Okay, and I would like to show you the following. If I have two vectors added, the transformation is as if you transform them separately and then you add them. Let me show you how this applies. Say you have three processes occurring in the frame of A. Say this is the process X, this is the process Y, and this is the process Z. These, let's call them events, X, Y, Z, event X, Y, Z. Say X and Y are separated by delta T1, delta X1, and Y and Z are separated by delta T2, delta X2. And suppose the separation between the X and Y is represented by the vector W1, and the separation between Y and Z is represented by W2. So here W1 plus W2 will represent the separation between the X and Z. So when I actually transform W1 plus W2, I'm transforming the separation between X and Z from the reference A to reference B. In other words, what I'm doing here is that the transformation of delta T1, delta X1, plus delta T2, delta X2, since this is the separation between the events X and Z, then I find the transformation to be the separation between X and Z in the frame of B. But in the frame of B, if we call them X prime, Y prime, and Z prime, if you transform the separation between the x and y as w1 prime and separation between y prime and z prime as w2 prime, then the separation between the x prime and z prime will simply be w1 prime plus w2 prime. So we can write down that the separation delta t1, delta x1 transformed plus the separation delta t2, delta x2 transformed. So note that here, this is the separation between x prime and y prime. And this one corresponds to the separation between y prime and z prime. So the sum of the two is naturally the separation between x prime and z prime. So that's what we would expect from this transformation to do when it's applied to the sum of these two vectors. So we have shown that if I add two vectors and transform them, it's the same as first transforming them and then adding them together. So this is the first thing we should show to say that this is a linear transformation. The second thing that needs to be proven is the following. A, some multiple of a vector W transformed must be the same as multiplying the transformation of W. Let's show that this is also the case for the Lorentz transformation. Say in the framework of A, you have two events, x and y, separated with delta t, delta x, and note that W is the vector delta t, delta x. In the framework of B, these events will be seen as x prime, y prime, delta t prime, delta x prime. Now, suppose we change the units, like suppose we're multiplying all the distances with some number a. Let me give you an example to make it more clear. Suppose I'm multiplying this with a scalar a. This means the following. Change all the distance, for example, from meters to centimeters by multiplying it by 100. So in this example, we're using a is equal to 100, but you can use any a value going from one unit system to any arbitrary unit system. So you're okay to multiply these numbers with some scalar so that you turn them into some other unit system. Now, the idea here is that if I multiply with a, meaning that I change the unit system and then transform that into the reference frame of B, what will happen is B will now see the things in the unit system, in the new unit system. So the transformed version of AW will be this time the same as TW with the change in units. So what we say is if, for example, two events are separated by 1 meter in the framework of A, and if they're separated by 0.9 meters in the frame of B, then this is the same thing as saying 100 centimeters to 90 centimeters. So I can first transform. So I can actually change the unit system and then transform, or I can change I can transform and then change the unit system. That would do the same thing. So we have shown that the transformation of AW is A times TW, which completes the proof. Thank you for watching me.